You and I use electricity every single day, but have you ever stopped to think about how it's actually measured? It's surprisingly tricky, especially when we're talking about the AC power that comes right out of our walls. So in this explainer, we're going to break down and really demystify the concepts of real, reactive, and apparent power.
You probably learned a simple formula back in school. Power equals volts times amps. Easy enough, right? So why is it that when it comes to the AC power in our homes and businesses, this neat little formula just completely falls apart? Well, that's the big puzzle we're here to solve today.
Okay, so with direct current, or DC, think of the power from a battery. Everything's nice and simple. The voltage and current are perfectly in sync, marching along together. That classic power equals volts times amps formula, it works like a charm. But with alternating current, AC, that's a whole different story. Things can get out of sync, and suddenly that simple multiplication doesn't even begin to tell you what's really going on.
Visit youtube.com/avidsystem and don't forget to subscribe.
So let's dive right in and start unpacking this AC power puzzle.
The reason AC gets so weird all comes down to certain components in a circuit. We're talking about things like motors, transformers, and capacitors. In an AC circuit, these devices cause the voltage and the current to fall out of step with each other. They become what we call out of phase. And when they're not working together perfectly, when they're not pulling in the same direction at the same time, poof, our simple power calculation is basically useless.
To really solve this, we have to stop thinking of power as just one single thing. Because in the world of AC circuits, there are actually three distinct types of power we need to get our heads around.
First up is real power. We call it P, and it's measured in watts. Now this is the good stuff. This is the power that actually does the work. It's what lights up a bulb, heats up your stove, or makes a motor spin. To make this super clear, let's use an analogy. Think of a big frosty mug of beer. Real power? That's the actual beer. It's what you paid for, and it's what you actually want to drink.
Next, we have something called reactive power, or Q. It's measured in a funky unit called volt-amps reactive, or VAR. People often call this wattless power, because it does no useful work at all. It's just energy that kind of sloshes back and forth in the circuit, building up the magnetic and electric fields that motors need to run. In our beer analogy, this is the froth. You know, the foam on top. It takes up space in the mug, but you can't really drink it. It's just there.
And that brings us to the third type, apparent power, which we call S. This is measured in voltamps, or VA. This is the total power that the utility company sees being delivered. It's the combination of both the useful real power and the not-so-useful reactive power. So back to our analogy, the apparent power is the entire mug, the beer and the froth, all of it combined.
So, how do these three different powers relate to each other? Well, it turns out they fit together perfectly in something called the power triangle.
It's actually incredibly elegant. Real, reactive, and apparent power will always form a perfect right-angle triangle. And this little visual model is the absolute key to understanding how they all interact.
Okay, so picture it. The horizontal base of the triangle, the foundation, that's our useful stuff, the real power. The vertical side shooting straight up, that's our froth, the reactive power. And then the diagonal line connecting them, the hypotenuse, that's the total apparent power, the entire mug.
And because it's a right-angle triangle, we can dust off our old friend from high school math, the Pythagorean theorem. S squared equals P squared plus Q squared. See? The total apparent power isn't just a simple sum, it's directly related to the real and reactive parts through geometry. It's math at work right in your electrical outlets.
All right, now that we have this triangle in our minds, we can finally understand the single most important metric when we talk about electrical efficiency, and that is the power factor.
So what is it? Simply put, power factor is the ratio of your real power to your apparent power. It's just a number, always between 0 and 1, that tells you exactly how effectively your system is turning electricity into useful work. Think of it as the ultimate efficiency score for your circuit. And let's bring it back to our analogy one more time. The power factor is literally the ratio of beer to the entire mug. It asks the simple question, how much of what I'm being supplied is actually the good stuff I can use? The perfect score, the absolute holy grail, is a power factor of 1.0, a perfect 1. This means your apparent power is exactly equal to your real power, which means there's zero reactive power. In our analogy, your mug is 100% beer and 0% froth. You couldn't ask for anything better.
So what do these numbers look like in the real world? Well, a perfect 1.0 is pretty rare unless you have a super simple load, like an electric heater. Most big industrial places are aiming for something between 0.85 and 0.95. That's considered good, or at least acceptable. But once you start dropping below 0.85, the system gets highly reactive and just really inefficient.
Now, I know this might all be sounding a bit academic. A number on a spreadsheet, right? But why does this power factor thing actually matter? Well, let me tell you, the real-world consequences are huge.
A low power factor is incredibly expensive in all sorts of ways. First, you've got wasted energy. The utility has to generate and send more total power just to get you the same amount of useful power. That means higher utility bills, and get this, power companies will often hit large customers with extra penalties just for having a low power factor. It also means you need thicker, more expensive wiring to handle the extra current, and it can even shorten the lifespan of all your equipment. It's a real problem.
So here's the bottom line, to bring it all home. A low power factor is like going to a pub, ordering a full pint, paying for a full pint, but getting a glass that's half full of froth. You're paying for energy that you can't even use.
So I'll leave you with this thought. Every motor humming away in your house right now, in your refrigerator, your air conditioner, your fans, is creating reactive power. So the next time you flip a switch, just consider for a moment how much of the power you're drawing is actually doing useful work, and how much of it is just froth.
Thanks for watching.